All right. First, I'd like to thank Maz and Binghai, organizers of this conference, for inviting me here and giving me the opportunity to talk about some recent work that we have done. And this conference has been great so far. I've learned a lot about Dirac fermions and YO semimetals. So the motivation behind our work is to build memory devices which are based on the controlled manipulation of magnetization using spin currents. And one of those example devices is the spin transfer torque magnetic random access memory, or STT-MRAM for short. So this device consists of a magnetic tunnel junction, which is two ferromagnetic electrodes separated by an ultra-thin tunnel barrier. Typically, we use MgO. And the resistance change that you typically get in this is somewhere between 100 to 300%. And you switch this device by passing charge currents through this device. And these charge currents can become spin polarized, and they can transfer their angular momentum onto another layer and switch it. And if you pass the current in the opposite direction, then you switch it the other way. And by forming dense arrays of this and combining it with CMOS transistors, you can form dense solid-state non-volatile memory devices. And this type of memory currently is under intense investigation by several industrial corporations. A related type of memory is the so-called racetrack memory, where you have a nanoscopic wire and you pass pulses of current in this wire and you move the domains inside of this wire, which are magnetized in one orientation versus another, back and forth along this wire. And this device also relies on spin angular momentum transfer to move these domain walls. And the more recent versions of this racetrack actually use this so-called chiral spin transfer torque mechanism, which does indeed take advantage of the spin orbit torque to move the domain walls back and forth along this wire. So the way that we generally generate this spin orbit torque is through the spin Hall effect. And the spin Hall effect, as our current understanding of it is due to the volumetric scattering of electrons throughout the bulk of this spin Hall material. The mechanisms to explain it are similar to what are used to explain the anomalous Hall effect in magnetic materials. So you use these side jump or skew scattering mechanisms, which are extrinsic mechanisms or intrinsic mechanisms related to the Berry curvature to explain why you get this accumulation of spins at the periphery of the material. Because it is thought to be due to the volumetric properties of this material, we thought that if we change the volumetric properties of the film, we should see changes in the spin Hall angle, and we wish to study that in order to see what the underlying mechanisms behind this were. So we chose a specific system to study, and that specific system was a tungsten film, which we doped with some oxygen. So when we introduced this oxygen into the tungsten film, we measured that oxygen content using Rutherford backscattering spectrometry, and we see that it monotonically increases with the amount of oxygen gas flow that we put into the film. Moreover, depending upon the thickness at which you grow this WO layer, the amount of oxygen that you incorporate into the film also changes. If you make it thicker and thicker, actually you incorporate less and less oxygen into your film. And this is due to the fact that there's a compressive stress which builds up in the film, which reduces the amount of oxygen that you can put into the film. So when we looked at the microstructure of these materials as a function of their oxygen content, we see that at first, when we don't introduce any oxygen into the film, actually you get an alpha phase of tungsten. By putting just a small amount of oxygen, you get the beta phase or the A15 phase of tungsten, and the A15 phase is a well-known phase of several superconductors. And if you introduce more and more oxygen, actually it becomes nanocrystalline. So in this way, by introducing those oxygen, we can controllably change the microstructure of our film. And likewise, the resistivity also increases. If you look at the resistivity versus temperature, it shows actually kind of a disordered and semiconducting-like behavior. However, in the cases where we do stabilize the A15 phase, you see an enhanced superconducting transition temperature, which is characteristic of that A15 phase. So before I go on to tell you how we measured this spin Hall angle, I'd like to review kind of the magnetization dynamics in this system, which are described by the Landau-Lifshitz-Gilbert equation. So this ferromagnet, it possesses about an effective magnetic field, and eventually it relaxes along to this magnetic field direction from a torque given by the damping. And when you introduce spin orbit torques into this system, actually these two spin orbit torques can act along either the direction of the torque given by the damping or along the direction given by the field. And for the technological applications, actually what you want to have significant is this damping-like torque, because this allows you to deterministically switch the device from one orientation to another in a controllable way. So this is what we're going to focus on measuring in as I'll show next. So the way that we measure this is we take a film that we grow like this, where we have this WO layer, then we put a ferromagnet on top of this. So this ferromagnet responds to the spins that we generate into this WO layer, and we measure the response of those spins by measuring this magnetization. We pattern this into a device. It's a micron size kind of wire like this. And the way that we do the measurement is we pass an RF current through the device. So this RF current is split kind of evenly between this WO layer and this cobalt iron boron layer, because the resistivities and the thicknesses of these two layers are comparable to each other. So when you pass this RF current through this device, then what happens is that you generate an oscillating spin accumulation in the WO layer. Now this spin accumulation will diffuse towards that cobalt iron boron layer and cause the magnetization there to oscillate. It's going to oscillate at the same exact frequency as the RF current that you put into the device. So you get an effect which is similar to how like a lock-in amplifier works, where you get a multiplication between these two components, and that gives you a DC rectification voltage. So the resistance of this magnetic layer changes due to the magnetoresistance, namely the anisotropic magnetoresistance in this magnetic layer. And by measuring this DC rectification voltage as a function of field, you're inquiring information about your magnetic sample. And so if you look at that data as a function of an external magnetic field, you see that it is resonant at a particular field for a given frequency. And you can fit this to some models which take into account the Lorentzian line shape. However, a more intuitive way to actually look at it is actually to look at the line width of this resonance. So the line width effectively describes the losses in this system, or the damping. So when we look at the losses in this system as a function of a superimposed DC current that we pass through the device, we see that it changes monotonically with the superimposed DC current. And the slope of this curve sort of represents a way to see the spin Hall angle. So the larger this slope is, that means the larger that you have your spin Hall angle, because you are changing your damping in your material much more significantly. So we looked at this as a function of the oxygen content in our films, and you can see the data as shown here. So what you see is quite interesting is that except for the film where you don't put any oxygen inside, you see that there is quite a substantial change in the line width as a function of the DC current. And if you convert this into a spin Hall angle, you get a trend that looks like this. This is the spin Hall angle as a function of the oxygen content. And except for where there's no oxygen placed into the film, the spin Hall angle actually is rather large. It's up to minus 50%. And actually for a conventional metal-based system, this is the highest that has been measured. And the only other systems where you get higher spin Hall angles than these are in, for instance, more exotic materials such as the topological insulators. However, when we looked at this data and we saw that it didn't change significantly with the oxygen content, despite the fact that we changed the volumetric properties of our films quite significantly, this sort of led us to think perhaps that it's not the usual bulk-like spin Hall effect that is taking place here, but there may potentially be an interfacial effect. So we decided to do some experiments to arrive whether that is indeed the case. So we looked at the first experiment that we looked at was to look at how does the variation in the thickness affect this spin Hall angle. And we measured that spin Hall angle as a function of thickness, and you see that it doesn't change significantly with thickness. But from my previous discussion, as I mentioned, the amount of oxygen content into your film is also thickness dependent. So if you actually take this into account, namely the amount of oxygen content change in your film, and consider that for films of different thicknesses, then you can also see from this that the spin Hall angle is not changing as significantly with thickness. However, this is not kind of a proof that our effect is actually interfacial in origin, because one can also say that this is due to the fact that you have a very short spin diffusion length. You would also see a similar trend in our data. To prove that it was an interfacial effect, what we did was we decided to disrupt the interface between these two magnetic layers. So before I describe how we did that, I want to review a concept which we've recently been using in our group, so-called transparency. So when you consider this the spin Hall effect and the generation of the spin accumulation and how it acts on the ferromagnet, one must also take into account that there is a impedance for the spins in going to the ferromagnet, and you have to take this into account, and it's quite important. And when you change the interfaces, one must also take this into account. And the way that we take this into account is actually we do an experiment which is kind of like the reciprocal of the experiment that we had previously done. So in the previous experiment, what we do was we took a spin current and we used that to act on the magnetization and cause it to precess. However, one can do an inverse experiment where one has the magnetization precessing, and one looks at how does the relaxation rate of the magnetization get modified in the presence of this non-magnetic layer. This is the so-called spin pumping mechanism that was also discussed in the previous talk. And by looking at how this change in this relaxation of the moment has changed or been modified due to this spin pumping, one can get the effective spin mixing conductance, as we call it, of the spins that go from this precessing ferromagnet into this non-magnetic layer. And this, you can think of this as though the non-magnetic layer is an additional kind of lossy channel for the spin relaxation that must be considered. So once we know this number, we can then go back and tell what is the transparency of the spins in going from the non-magnetic layer into the ferromagnetic layer. So we do this, and we arrive to the transparency of our films. And we look at this for different material combinations, namely when you have no insertion layer in between. This is the effective spin mixing conductance as a function of the oxygen concentration. And then we put deliberately different layers of materials in between, namely a copper, gold, and a titanium insertion layer. And this is how the spin mixing conductance varies as a function of this oxygen concentration. And we can use this actually to derive directly the transparency of the spin flowing into this magnetic layer. And once we know that, we can actually back calculate what should be the spin Hall angle if it was a bulk-like effect. And we've done that. So here is the spin Hall angle as a function of oxygen concentration. I took the absolute value of it so that it's a little bit more intuitive to see. And then I looked at the data with the copper insertion layer, and here's what I would calculate based on a bulk-like understanding of the spin Hall effect. I do the same thing for a gold insertion layer and a similar thing for a titanium insertion layer. So if my spin Hall angle is completely due to a bulk effect and not due to an interface effect, the experimentally data I should measure should line exactly where these open symbols are. And the black symbols are when there was no insertion layer placed in between. Experimentally, when I measure this, I see that it is actually very significantly different. And this is what proves that this is an interface effect. And I see this also in the gold layer and also in a titanium layer. Only the case where there is no oxygen inside of the film is the open symbols and the closed symbols match quite well. And this is what proves that the effect that we observe is indeed due to an interface. One can also say that this effect might be due to the fact that when we dope oxygen into this tungsten, some of this oxygen might be migrating towards the cobalt iron boron layer. So we did another test where we took a pure tungsten layer and oxidized the cobalt iron boron when we deliberately grew it, and we saw that the spin Hall angle that we measured there is actually more along the lines of what we would get for the tungsten layer, namely minus 10.23%. So that also proves to us that it's not the oxygen migration into the cobalt iron boron layer which is causing this effect. So for the later part of my talk, I would like to now kind of focus on what are the applications that you can do using this now that you have this kind of enhanced spin orbit torque. So if you recall from our earlier discussion, the way that we switch normally a magnetic tunnel junction is you start with unpolarized charge currents. Let's say you have equal numbers of spins pointing up and down, and you pass this through a ferromagnet. So then upstream, you would get some spin polarized charge currents. And if you have sufficient number of these spins acting on a ferromagnet, you can cause these moments here to reorient themselves, and hence the charge current going upstream of this will become polarized now in the same direction as this ferromagnet. So you can use a similar kind of concept here now for switching a spin Hall material, except you create the spin accumulation through the spin Hall material. So if you have a magnetic tunnel junction on top of a spin Hall material, you can now switch this by just passing a current onto this bottom spin Hall material, and the spins that are generated here will accumulate and flow into this layer and switch it. So we have made devices like that in order to see this switching process based on our oxygen-doped tungsten layers. So we have a magnetic tunnel junction, and the resistance versus field is like this. You have two stable states, the anti-parallel and parallel states, and we can switch between these two states just by simply passing a current into this WO layer. And the first test that we did was to look at how does this switching field between these two states change as a function of a DC current through that oxygen-doped tungsten layer, and you see that you can modify the switching fields quite significantly. Moreover, the switching fields are modified in a way that is consistent with the spin accumulation that you would generate in this WO layer, which is opposite to that of generated by a Ørsted magnetic field generated into this layer. And after that, what we decided to do was we turned off the field, and then we looked at the case if we could switch the magnetic tunnel junction completely just by current. And we are able to do that. And actually, you can do this as a function of various pulse lengths, and this is in what is called the thermally activated regime of the MTJ switching. And by extrapolating this to a zero pulse length limit, you can get kind of like a zero temperature switching current density for switching the magnetic tunnel junction. And we find that our switching current density is actually 2 times lower than what you would typically expect for the tungsten film, beta tungsten film, which is also consistent with the larger spin Hall angle that we measure. So we also have been able to use this actually in racetrack memory devices. So the existing racetrack memory devices were based on using cobalt-nickel multilayers on a platinum underlayer. So when we pass pulses of currents through this, you can cause these domain walls to switch back and forth. This is measured using a Kerr microscope. So it's a microscope that has magnetic contrast. The polarization of the light changes slightly depending upon the magnetic state of our wire. So our previous data was in this regime. And for one of the technological drawbacks behind being here is that the critical current density for moving the domain walls was very, very high. It's on the order of 10 to the 8 amps per centimeter squared. And by switching to this tungsten oxide layer, we were significantly able to reduce the switching current density of this device. And this is a very exciting prospect for making racetrack memory devices technologically viable. So now I'd like to also discuss a few other kind of devices, kind of logic devices that one may also be able to build using these similar concepts. So this is actually a wire where the magnetization lies in plane, and all the magnetic moments can curl around and form these vortex-like structures, which are either clockwise or counterclockwise. And actually, the operation of this device can be thought of in a kind of a topological way. So the chirality of these domain walls corresponds to a spatial arrangement of the topological defects that of the order parameter of the magnetization in this device. So and the way that the domain walls propagate is due to interaction of the topological defects that are forming in the domain wall and the innate topological defects that are part of this structure. And if you apply a magnetic field to move these two vortex domain walls, depending upon their chirality, they move in one branch or the other. So in this way, you can build kind of a 2-bit demultiplexer device where the chirality is the selector bit, which chooses which branch the the domain wall moves. And we can also do similar things where we move them by using spin orbit torques. And these are moved by using currents. And in this system, actually, we have chiral domain walls because we have this asymmetric exchange interaction, namely the Dalazinski-Maria exchange interaction, or the DMI. And this locks the chirality of the domain walls. So you have neo domain walls in these systems, and the up-down domain walls have a set chirality, have a set polarity as well. Namely, they point towards the right, and then the down-up ones points towards the left. And if you have an up-down and a down-up domain wall, they actually move in two different directions. And by using different pulse sequence, you can actually have them either sort or be split into two branches as shown here. And this is experimental data that's also taken on a Kerr microscope. Lastly, I like to also show that you can build these types of devices. This is where we have a magnetic wire, and then we have made one part of the wire actually point in plane, and actually we can use this to inject a whole series of domain walls into a racetrack memory device. So this injects it at actually a very steady stream here. This is using a DC current, but if you have an arbitrary pulse sequence, you can put any data stream that you want into the memory device. And one can also build gigahertz oscillators based on using these spin polarized current concepts. So this is a nanowire which is pointing where the magnetization is pointing perpendicular, and you have one part of the wire where the magnetization is pointing in plane, and using spin torque, we are able to excite this region and cause it to process at actually gigahertz frequencies. And by building dense arrays of this, you can actually cause them to all kind of phase lock to each other. This is also based on using spin torques. And so all of these devices I've shown you, actually, we have also experimentally demonstrated, although these are simulations. The only one that has not been demonstrated experimentally is actually this nano oscillator. And that brings me to the conclusion of my talk. So we've been able to show spin orbit torques, which are in a conventional metal-based systems that are largely interfacial in origin and have a magnitude of up to -50%. And and we've seen evidence that it doesn't scale with the bulk or volumetric properties of the film. And then also see that it is quite useful for some important applications such as MTJ switching and racetrack memory devices. And if you'd like to learn more about this work, a large fraction of it is in this paper published in Nature Communications. And I finally like to acknowledge that this work was not done by me alone, but was done with my colleagues at the IBM Almaden Research Center. And actually a large fraction of the work was done by a visiting student in the group from the Technical University of Dresden. And with that, I'd like to thank you for your attention.